Good. Today is Wednesday, the 30th of April. We are about to start chapter 24. There is just one more thing that I want to tell you about chapter 23. Let's see what's going on here. And then chapter 24 is going to be mirrors, right? Mirrors. Week number 12, and let's take a look at our notes. Meeting number 19. Last thing we want to talk about. Last thing we want to talk about is intensity of an electromagnetic wave. Okay, we talked about energy of wave, energy of the electromagnetic. Let's put electromagnetic wave, right? We talked about energy density of an electromagnetic wave, and now related to energy density is the concept of intensity of an electromagnetic wave. It's a very important concept that we see almost everywhere, okay? And this intensity of electromagnetic waves, also called the pointing vector. Let's see, the pointing. Let's see how this is spelled out. Pointing vector, yeah. Okay, it's with Y. Okay. Pointing vector represented by the letter S. This is actually a vector, but we are not going to worry about the vectorial quantity. We're going to worry only about the scalar quantity associated with the pointing vector, okay? And then we have to clarify what intensity means, okay? We have to clarify what intensity means, okay? Going back here to your book has a very nice, simple way of definition. The intensity is the power, okay? Is the power that passes through a surface divided by the area, and the area that we're talking about is an area perpendicular to the direction of propagation of the electromagnetic wave, okay? It's a very useful quantity. The definition of intensity is the power per unit area perpendicular to the direction of propagation of the wave. Propagation of the wave. Okay, so there's a rather simple way of illustrating that. Let me go back to my other one. Reflection mirror, this one here. So let's say we have this this illustration, right? The direction of propagation of the wave is along this x direction, but the electric and magnetic field are perpendicular to all those three. Okay, so to each other. So it's gonna be like that. I'm gonna have here the electric field. Gonna have here, let's say, the electric field, right? The magnetic field is represented by the circle with a tip there at the center of the field of the circle, like that. And the direction of propagation is going to be perpendicular to both vectors. Okay, here you go. And the pointing vector that I mentioned to you, right, is the specify the direction of propagation of the wave. Let me get everything here so we can make it look nice. Okay, here you go, the vector electricity vector. I'm going to label that there in the drawing. I'm going to even put that in a different color, so it becomes easier to visualize, right? Let's put the electric field in the red color. Okay, so we gotta put it this way. Here you go, the electric field. This one, I'm gonna put it in blue color. Heavier weight, here you go. And this one here, gonna be my magnetic field. And this other one here is going to be my pointing vector. The pointing vector, like I mentioned, tells you the direction of propagation of the electromagnetic wave. And note that is going to be E cross B, right? If you apply the right hand rule, when we orient the palm of our hand in the direction of the electric field and curl the hand towards the magnetic field, the right thumb points in the direction of the propagation of the wave. That's what you have to know. We usually represent that by a cross vector across. Let me write that down here. More. The definition of intensity is the power per unit of area perpendicular to the direction of propagation of the wave. The direction of propagation of the wave is given by the right hand rule. Right hand rule. In the following way. One, you point the palm of the right hand along the electric field. Two, curl the palm of the right hand towards the B field. And 3, the direction of propagation of the wave. Here you go. The right thumb points in the direction of propagation of the wave. Okay. This direction is given by the pointing vector. Its magnitude represents the intensity of the wave, like that. Like that. Okay, Justus is trying to come in. Can you remember that? Okay, so right in here, right? If I were to come up with a different pointing vector, here you go. Let's come up with a different pointing vector or a different electromagnetic wave, right? Here you go. Let's say, suppose the electric field instead of upwards is downwards, right? Suppose it's downwards like that. So you go ahead and you do the right-hand rule. I'll put my B field right in here, and then what you end up having? You end up having a pointing vector that's going to be in the other direction. Oops. Here you go. E cross B, right? And you could do the same for the B field going downwards as well. Here you go. Let's do the other case. Now the B field instead of a dot here. And I'm going to choose something else. Let's see. Okay, this one that I want. The B field pointing into the board. Oops. Like that. Fill, and I want to fill with white, but then I want everything in blue, right? And I also want to make a little bit thicker, make it look nicer, like that. Okay? Oh man, now I have E cross B should make the vector point in the other way. Here you go, should be this, the vector propagation gonna be on the other way, and send back, and I can erase this one here. Okay, and the other one, you know, the fourth possible direction would be if we put this vector here, upwards. Like that. Then I have to E cross B. Oops, the B should be downwards here. And I have to revert the S direction as well. Here you go. Okay, direction of propagation of the electromagnetic wave. Electromagnetic wave. But we gotta do more than that. Not just the direction of propagation. We gotta also come up with the formula for the pointing for the intensity or the magnitude of the pointing vector, right? So definition. S. S is defined as the power per unit of area. And let's not forget that the power is the energy per unit of time. And I'm going to do some nice mathematical. I'm going to even put a delta U over delta T, okay? Delta U over delta T. I'm going to do some neat mathematical trick here that's going to allow us to come up with a better equation for what you see right in here. Okay? So I'm going to use this one here instead. Let's use this one here. Number is trying to come in. Okay. Okay, so let's see how I'm going to do that. Well, I'm going to show you in the book, so I don't have to make a drawing here of the whole thing. So let's see. Yeah, okay. Here you go. Here's a drawing, right, of the electromagnetic wave. Here's the area A. Okay. And this area A has a small thickness that should be C delta T. Okay. What C delta T is? The velocity. C is the velocity of the wave times T. So Ct is going to be the thickness that the electromagnetic wave goes through, the distance that the electromagnetic wave travels in amount of time T, or delta T in my case. Okay. So if this thing here is the area, what you're going to see here, is going to be the volume, the whole volume of the electromagnetic wave, where the electromagnetic wave is enclosed, okay? The volume the electromagnetic wave travels in an amount of time delta T, okay? So if we go ahead and multiply the top by C, which is the speed of the electromagnetic wave, and divide the bottom by C, we have the same equation, but we are going to have as well the same equation displayed in a different format. C delta T is going to be by delta X, okay? And now that I have area times delta X, I'm going to have here the volume V. I'm going to put lowercase v. Delta U over V for volume, right? Not velocity, but V for volume. Delta U over V is something that we already know. And by the way, we should put that delta V instead, because we're multiplying by delta X. Okay? This delta U over delta V, we already know what it is. Okay? Is the energy density of the wave, which we calculated before. Let's go back here, the energy density. The energy density of the wave is this one right in here. Proportional to the square of the electric field. U, right? Which is going to be C equals C epsilon naught E squared, as a function of time, right? But then we can get also the average, the root mean square average. Okay, and that's what.
Month I've spent $4,232.74.
On what?
Let's see here. Manuel
Rent?
okay, looks like Manuel accidentally start talking here. Turn on the mic. Okay, Manuel, so here you go. And we can here write, right? Here you go. Here's the intensity of the wave. We can here write it in a slightly different way, right? And don't forget that this C, remember there is a relationship between C and those two constants. Those important constants that we saw, here you go, epsilon naught, and then we're going to do mu naught. Remember that relationship, okay? And there's a relationship between E and B as well. Okay, let's take a look. Okay, right in here. Here you go. That's the relationship between E and B. Right? We didn't derive that. We didn't derive this relationship. We cannot derive that because the level of mathematical level of this course doesn't allow to do that. But just remember, just remember that for an electromagnetic wave, the energy density of the electric field is equal to the energy density of the magnetic field. Just remember that. Okay? If you remember that, it becomes easier to remember to derive the relationship between E and B. It's gonna be something like that. Okay. And let's see how we can here write that in terms of the magnetic field. To here write that in terms of the magnetic field, we have to write E in terms of B, like that. Here we go. So the next step, well, in reality, we didn't need to do that, but I want to show that to you so you can remember the relationship between C, right? And those other two important constants. Okay, so let's continue working with this relationship here. We got a square, this term. Okay, we end up with the square of the C and the square of the B. Let me remove the time dependency here to shorten the notation. Okay, we have to do, oh, we can do one more step here. Don't forget that this C square is going to be equal to this ratio without the square root. And I can take away the boldface. We will be able to cancel the epsilon naught in this equation, epsilon naught here. And we got the b square over mu naught times c, right? B square c mu naught b square. I like this format. Let's put the format according to the book, because all the constants end up in a single fraction, right? There are other ways to rewrite this equation, right? Yeah, but this one is the best way. Would be the best way to write it, okay? So this equal to this equal to the other one. So that's what we have for this chapter. And now we can go to the next chapter. That's going to be chapter 25, reflection of light mirrors. Okay, that's a nice chapter 25, reflection of light by mirrors. The theory that we're going to use here, the theory we will use here is called the geometrical optics. The theory of geometrical optics. Geometrical optics. Okay. In geometrical optics, we represent the light as light rays. Okay, and the light rays which is represented by an arrow. Okay, so just like we did for the pointing vector. Okay, going back here, because in geometrical optics, you know, instead of keep on drawing those vectors right in here, we simplify the drawing of propagation of the wave, of the electromagnetic wave, just like we represented the propagation of regular waves. We represented by a straight line representing the front of the wave. Okay, so here you go. I'm gonna put it in black color. This front is actually a plane. Okay, is a plane that I didn't draw, but I can draw it here for you. Let's see if I can do that with this one. Let's see. No, not this one. I want to do another one to give you the illusion that the two-dimensional. Let's try this one here. No, okay. I'm going to do like that. Here you go. And then I will be able to rotate. Format. Rotate. RL is coming. No, that's not what I want. Don't want to rotate like that. Let's see. Rotation scale height. There is a way to rotate that in the three-dimensional space. I can't seem to remember how to do that. Let's see. Size and position. Let's see. No, not this one. Let me try format shape. 3D rotation right in here. Okay, good. I got what I want. Let's try this one here. See if that was, yeah, okay, good. That's along the x-axis, right? So, and I'm going to bring this vector here to the top. I'm gonna bring this one too. Bring to front. Here's the midway. Here's my vector, my pointing vector, the vector of propagation of the source. Let's see if I can do better than that too. Let's see here. No, not this one. It's this one that I want. Format shape. No. 3D rotation. Okay. Now let's see if I can go. Yeah, here you go. Now I finally getting there, right? Give the illusion that we have a three-dimensional drawing here. A three-dimensional drawing. So, and to come up with even a better way, what I'm gonna do. Bianca is trying to come by. Hello. Here you go. And then I'm gonna dash this guy here to give you the illusion that what we have here is a front wave, the wave front. I'm looking from the back of the front of the wave, and here are the coordinates. Can you picture that? Yeah, here you go. And now I'm gonna and then you can have multiple fronts representing what this front represents. This front represents the electric and magnetic fields. Okay, I can even go ahead and picture the electric and magnetic fields right in here using the right hand rule. So right in here, I would have, I'm gonna just draw the electric field. I don't need that, okay? Here you go. Yeah, here's the electric field. And then I'm gonna draw the magnetic field. I'm gonna use this pointing vector here. This pointing vector must be perpendicular to the electric, this pointing vector. This other vector, this magnetic field vector, supposed to be perpendicular to the electric field. And the pointing vector is perpendicular to both fields simultaneously, okay? And I'm even going to illustrate that again. Here you go. By two colors, two different colors, one blue, the other red. And like I did before, usually I inverted, right? But that's okay. Let's see here. Okay, let's make it the horizontal vector, the electric field vector, okay? Like that. And I'm gonna hit position like that. Oh, it cannot be this direction, right? It has to be the other direction. Otherwise, it doesn't obey the right-hand rule. You gotta put the B field downwards. Let's see. E cross B, yeah, E cross B points to the right, okay? E cross B points to the right. Another way that, a simpler way to represent that instead of doing all this math that I did, right? We can just represent the front of the wave as a line. Now we are looking into the electric field. I'm going to remove this guy. I'm going to remove the other ones. I don't need that either. I don't need the dash anymore. And I'm going to need this one here in the red color. Not this one here in the red color. Yeah, here you go. Okay. Oops. And what we call the front of the wave can be drawn as a plane that contains both the electric and magnetic field vectors. I'm going to draw this plane as though as a black line. You go. No, not this one. This one right in here. Yeah, better. Like that. He go black seeker. And what I'm going to do, I'm going to get this vector that you see right in here, and I'm going to bring to the front. Oops. Okay, I gotta put it back. Just bring to the front. Yeah, okay, good. That's the plane that contains the electric and magnetic fields, right? And that's the direction of propagation of the wave. We can depict several fronts of the wave. And the pointing vector is going to be the light ray. That's what we call the light ray. Okay? That's good. So instead of drawing all those vectors that you see here, we just represent the front of the wave that contains the electric and magnetic fields. Okay? In geometrical optics, we represent the light ray as vectors, as an arrow, okay? As an arrow. As an arrow. This arrow shows the direction of propagation of the light ray that coincides with the direction of the pointing vector, with the direction of the pointing vector. Okay, and we all pointing. We also draw a plane that contains the electric and magnetic fields. Okay? Like that. Here you go. This plane contains electric and magnetic field. This plane contains electric and magnetic field. This other plane also contains electric and magnetic fields. I'm going to copy that and paste in my other slide, PowerPoint slide. Okay. What else you have to know? Okay. Let's say that our source is a point source. Electromagnetic source is a point source. Our light source is a point source. Okay, so here are the representations of the direction of the light rays that propagate from the source in all sorts of directions, right? Here's my pointing vector that I mentioned, that right now we're going to treat it as though it's just a light ray. And if you have not a point source, but a distributed light source, the light rays are going to propagate normal to the surface of this source, okay? And we're going to talk about mirrors. That's what we're going to talk about. Here you go. Here we have a representation of a planar mirror. Okay, that's a representation of a planar mirror. And here is my point source next to my planar mirror. A light ray that propagates from the point source to the mirror can be reflected by this surface. Can be reflected by this surface. And there is a very important relationship for the reflected light ray and the incident light ray, okay? How do you find out the incident light ray first? Okay, there's an angle for the incident light ray, and the angle of the incident light ray is taken with respect to the normal of the surface of the source of the mirror. And there is a very important law, so-called law, between quotes. It's not exactly a law, but just a consequence of something else more powerful, okay? It's called the law of reflection. This dashed line is perpendicular to the mirror, okay? Normal to the mirror. And the angle of incidence is measured with respect to this direction, that is perpendicular to the mirror. The angle of incidence, we call it. Okay, there is this important result in physics, that whenever a mirror reflects a light ray, the angle of reflection of the light ray is going to coincide with the angle of incidence of the light ray. Can you remember that? Okay. Many people call that the law of reflection. It's not a law. It's actually the consequence of something else far more powerful that we call the law of least time, the principle of least time. Principle and law, they mean exactly the same thing. Okay, remember that? I'm going to write that down for you. In geometrical optics, geometrical optics is a very powerful theory, by the way, and very simple too, because just use geometry. In geometrical optics, an incident light ray is reflected at an angle equal to the incident angle. This result is called the law, I'm going to put it between quotes, of reflection. The law of reflection. This is not an actual law. Instead, it's just the consequence of something else called the principle of least time. Okay? The principle of least time. So light rays obey this principle. It's just like to say that, light rays are always in a hurry, right? Light rays are always in a hurry. So you want to go, a light ray wants to go from one point to another in the least amount of time. That's what it means. In other words, light rays want to go from one point to another in the least amount of time. Okay, that's what the principle of of least time is all about. I'm going to illustrate the principle right in here. So here you go. Suppose that we have, let's see if I have an illustration here. Yeah, it doesn't look like I have an illustration here. Okay, the principle of least time, okay? So I'm gonna use this situation here. So we have a light ray coming out from this point, okay? And let's say, here's the source, and then this light ray is gonna pass through another point. That is this point right in here, P. The reflected light ray is gonna pass through another point at this point right in here, okay? So the question is, what's the path that this light ray is gonna take? That's the question that you have to ask yourself, okay? The path that this light ray is gonna take is gonna be from here to here, okay? It's gonna take, the path of this light ray is gonna take another different path from here to here, right? I'm gonna put that in different colors. Yeah, here you go. And I'm gonna make it thicker too, so you can see it better. So there is this infinity number of paths that you can have here. infinite number of possible paths, okay? So here you go. There's this other possible paths. Now, I gotta do it a different way. That's another possible path. Okay, so the question is, which path does the light ray chooses to go? Okay. Okay, the path that the light ray chooses to go is the one that takes the least amount of time. And which one takes the least amount of time? Okay. Is it gonna be this one? Is it gonna be this one? Is it gonna be this one? Or any other possible one? Okay. Well, we can come up with a derivation, and then we find out the path that takes the least amount of time. Light rays travel at the speed of the light, remember, is going to be exactly this one that in which the angle of incidence is equal to the angle of reflection, okay? That's what the principle of least time is all about. Okay, and I'm going to spell that out here for you. In the principle of least time, consider the following. Consider the following. One, a point S, which is the position of the source of a light ray. A point P, which is the position, a position which is a position where a reflected light ray from the source passes through, okay? Consider the following. There is one more thing here left that I should have put it first. Consider a mirror, a planar mirror. Point S, which is the position of the source of a light ray. Point P, which is a position. Point P is a position where the reflected light ray from the source passes through. Okay. According to the principle, of least time, the light ray will choose a path from S to the mirror and to point P that takes the minimum amount of time, okay? The minimum amount of time. Applying this principle, we find that it is satisfied whenever, the angle of incidence of the light ray is equal to the angle of reflection of the light ray. Reflection, right like that, okay? The above result, and I'm not going to, this one is kind of, actually this one is kind of easy to derive, okay? All you have to do is to find which one is the least amount of space, okay? This length plus this length is going to be less than this length plus this length. It's going to be less than this length plus this length, okay? Because this we are dealing with an homogeneous medium here in which the velocity of the light is the same everywhere, right here. It's possible to prove that this length plus this length is going to be less than any possible. It's going to be less than the length of any possible path. Okay. For a light, okay. The above result is usually referred to as the law of reflection. Strictly speaking, this is not a law, but a corollary or consequence of the principle of least time. Okay. In the case of light propagating through an homogeneous medium, and by homogeneous medium means the velocity of the light is the same throughout the entire path of the light ray. That's what it means. The principle of least space, okay, coincides with the principle of least time, okay? In this specific case that we have the situation in which the velocity of the light is the same throughout the whole space, the whole volume of propagating of the light ray, the principle of least space, okay, coincides with the principle of least time, okay? In other words, under this condition, under this condition of homogeneous medium, light also chooses the least distance or space, right, to travel from one point to another. Make sense? Okay. And then we can prove that easily. I'm not going to do that, but hope you to believe that. Okay. What time is that? 10:40. Okay. So let's take a quick attendance here. Today is the 25th, and lab gonna be lab number 5. Abir Ahmad, are you there?
Yes, I'm here.
Okay, thank you. Next is going to be Nestor Alvarado.
Here, I'm here.
Thank you, Nestor. Monte Ambarchian. Let's see, Monte. I don't see Monte here. Okay. Next, Isabella Ballesteros.
Here.
Thank you, Isabella. Justus Bowden.
Here, Professor.
Thank you. Alexandra.
I'm here.
Thank you. Benjamin Carvajal. Thank you. Elizabeth Castellano. Hello, Elizabeth. Okay, I'm going to put a star here. Elizabeth. Natalia Cordoba. Thank you. Next is Jacqueline Delgadillo. Hello, Jacqueline. I see Jacqueline here in my roster, but I don't hear from her. Let's go for the next one. Jenny Diaz.
Here.
Thank you. Valerie Diaz.
Here.
Thank you. Next, Juan Escalera. Thank you, Juan. Bianca Yoloki.
I'm here.
Thank you. Edwin Gonzalez. Next is Eli Gonzalez.
Here.
Thank you. Manuel Hernandez.
Here, Professor.
Thank you. Samantha Hubert.
Here.
Thank you. Next is CJ. CJ looks like CJ disappeared, right? CJ Houghton. Okay, let's put this. Next is Amber Lopez. Hello, Amber. Okay, I'm gonna put a star here for Amber. Arely Lopez. Okay, thank you, Arely. Genesis Lopez. I don't see Genesis here. Let's see. Monte is just joining us. Mary Michaelian.
Here.
Thank you. Galia Udabashan. I don't see Galia. Okay. Okay. Monte, are you there?
I'm here, Professor.
Okay, thank you. Next, Ramon Olivares.
Here.
Thank you. Taylor Thorne.
I'm here.
Next is Jeremy Pittman. I don't see Jeremy here. Stephanie Ramos. I see Stephanie in my roster. I don't hear from her. Leslie Alexandra Rios. Leslie Rios. That's Leslie, right? Okay. Yeah. Okay. Jason Strait.
I'm here.
Next, Gemma Torres.
I'm here.
Next, okay, so we are done with attendance, 23. Okay, good. So let's take our break. And that's a good point to stop. Do you understand the
Hello,
principle?
Professor.
Yeah, what is that?
Sorry, I'm here too.
Okay, who is that? Who is speaking?
Jacqueline Delgadillo.
Okay, Jacqueline, okay. Delgadillo, right? Delgadillo,
Yes.
right in here. Okay, so I'll call you folks again and give you an opportunity to fix this star here under your name, okay? So let's break from 10:46 a.m. to 11:01 a.m., okay? I see you shortly. Stop sharing. I am back here. Let's start sharing the screen. Okay, so this is a good point to stop here on this topic, on the lecture, okay? We are going to go back to that next time. Now what we're going to do is lab 5. Lab 5, circuits with 2 resistors. That's what this lab is all about. Now, you should be able to download your spreadsheet. Let me know. I wasn't able to correct your lab number 3, but I will be doing that soon. Okay, once I have corrected, I'll post that I'll post the correction in Canvas as well as your grade. Okay. Now let me, that's, okay. Benjamin start trying to get in, right? Let's go back to our syllabus here, right? Yeah, it's lab number 5, 2 resistors in a single circuit. Okay, here we go. So Ohm's law is circuit is 2 resistors. You know, that's 2 Ohm's law. And make sure you download your spreadsheet, right? And I'm gonna open one of my spreadsheets to walk you through what we have to do. Okay, so here you go. Here is one of the spreadsheets that I have. Notice that we have a table for 2 resistors, right? And a table similar to what we did before, but now it's a little bit more complicated because we are going to have V1 and V2, right? We didn't have we had only V1 previously because we had only one resistor, but now we have 2 resistors. Because of 2 resistors, the electric potential is split between one resistor and another one. Okay, and let me. So the objective of this lab is to verify Ohm's law experimentally. Okay, here you go. That's objective. Verify Ohm's law experimentally using a circuit with 2 resistors in series. Okay. Materials and equipment. We are going to need at least 2 resistors. We start with 2 resistors. Here you go. Here you go. The value of the resistors is given there in your table. In my case, the the resistor that I have here is around 3,000 ohms. One is around 3,000 ohms, the other is around 400 ohms. Okay? Procedure. What's the procedure? We are going to measure the resistance of the two resistors separately with a DMM. Okay, so here you go. That's another material here, digital multimeter, right? Digital multimeter, DMM. In case you do not remember, let me show you. Okay, here is a multimeter of mine. Okay, they look like, there are several different multimeters out there in the market that I mentioned to you. Okay, and it has a dial here that allows you to measure different types of quantities. Here is AC voltage. Here is DC voltage. Let me stop sharing, just to refresh your memory, right? I have shown that to you before. Let me show you it again because I consider that very important. Let's see. Okay, good. Now you should be able to see my multimeter. Okay, so here you go. In this case of my multimeter, you have an off button, volts AC, volt DC, and then you have a scale of millivolts as well for volts. And then this multimeter is kind of fancy. Cost me like $300 at the time. Maybe it's more expensive now. It also measures the frequency of a circuit. Not every multimeter has this capability, but most multimeters has those volts AC, volt DC, and a scale to measure resistance, ohms. Okay. On the other side, here we also have this one. Like I said, since this is a fancy meter, you can also measure temperature. Okay. On the other side of this scale, we can measure current. Okay, high current at 10 amps, and current at milliamps, and different scales for the current, microamp, milliamp as well, and amps. Okay, the left side is current, the right side is voltage, ohms, and frequency, plus temperature as well. If you are measuring voltage, you use this path of the circuit. Okay, you're always going to use the black cable that goes in the COM. COM stands for common, and the red cable that goes in the measurement of voltage. If you measure volts, if you measure ohms, if you measure temperature, they are all the same circuit. So you use right here at this one. But if you're measuring current is a different beast, okay? It's a different beast in terms of measurement. You have to use a different circuit. Why is that? Because this circuit here is for measurement in parallel, right? Whereas whenever you're doing current measurements, you have to put your multimeter in series. That's why we end up having to plug this cable in a different jack here, in a different connector. That's because you are using a different circuit. And it also applies to high current. Here is low current, and here is the circuit for high current, 10 amps. Okay, they build a different circuit for a higher current. So here you go, procedures. Now we have three devices, right? Two resistor plus one digital multimeter. The idea is to measure the resistance. The idea is to verify Ohm's law, and the first thing that you're going to do is to measure the resistance of each resistor with the DMM. And that's what we have right in here. I'm gonna highlight with yellow. Whatever is yellow is the measurement, is your measurement. I will blur my background, and I also going to share my screen. Here you go. Okay, so whatever is highlighted in yellow is going to be our measurements. Okay, to measure the resistance of each resistor, all you have to do, let's see if I did that here in my slide. Oh yeah, here you go. All you have to do is to set your multimeter to measure resistance and get the probes to touch the two leads of the resistor, resistor 1 and resistor 2. Okay? And you write down the voltage in there, the resistance there in the table. In the next step, we are going to put the circuit together. We start with the power supply. Let's list the power supply here as well. List of the devices. Power supply. Okay. Turn on power supply to adjust power supply to 10 volts. Adjust power supply to 10 volts. Just like we did in the previous experiment, right? Okay, red cable, red banana cable in the positive jack of the power supply. Red banana cable, plug it to the red jack, positive terminal of the power supply. And I'm going to write that down here for, let's start with one red banana cable, right? You're going to need more than that, but let's start like that. And as we go along, we are going to draw the diagram, the schematic diagram as well. Here's the battery, representation of the battery, right? And let me do one more thing here. Power supply, I'm going to eliminate that. There is one more step, right? Here you go, like that. Here's the power supply. Here is the power supply as well, in a schematic fashion. Now, red cable, this is the red cable here. This line represents the red cable. And then we're going to put resistor 1 in series with resistor 2. Okay? So connect the other end of the red banana cable to the lead, one of the leads, to one of the leads of resistor 1, and then using, an alligator clip. So we're going to need at least one alligator clip. As we move along, okay, I'll be adding on those numbers here. One alligator clip. We're not making any measurements whatsoever. Not yet, right? Not yet. We're not making any measurement yet. Here you go. Here's my circuit. Here's the symbol of the resistor, right? Next, we are going to connect a second resistor in series with the first resistor. And we connect the second resistor in series with the first resistor using a prototype board right in here. Okay, one is the resistor 1, the other one is resistor 2. So we go. We're going to need a prototype board. Prototype board. Connect. Connect resistors 1 and 2 in series using the prototype board. Using the prototype board. Here you go. Then we close the circuit with the black cable, with the black banana cable. Okay. Here at this end, we are going to need an alligator clip. At the other end, you do not need an alligator clip because the banana fits well into the jack, into the banana jack of the power supply. Okay, so prototype board, 1 black banana cable, and 2 alligator clips now. Use the second alligator clip, right? Use the second alligator clip to connect the black cable to the second lead of resistor 2. Connect the other end of the black cable to the negative terminal. Is going to be the black jack of the power supply. And here you go. We have our circuit ready. At this very moment, electric current is flowing through this circuit. Okay, here you go. You have, let's say, positive charges flowing along the circuit. They move through here and there. It's very important that you can envision what's happening at the microscopic level, right? You go. More. You go. And then we have those other 2 charges. I'm going to put on the other side. Don't forget to change the direction of the current, right? And we are going to change the direction of this current, of this arrow. And here too, right? In this diagram as well. The circuit is closed and current is now flowing through it. The first thing that you're going to do, you're going to measure. You're going to take the next thing, not the first thing. The next thing you're going to do, you're going to measure the voltage across the circuit. You start with the total voltage. Okay, here you go, multimeter. Next, we will measure the voltages in this circuit. The first voltage is going to be total voltage. Measure the total voltage. Voltage across resistor 1. Voltage across resistor 2. Okay. So in order to do that, we are going to need 2 more cables. Okay, we're going to need 2 more cables. Well, one black and the other one red. So my multimeter is right in here. Let's see what's going on here. Okay, this one is just repeated for some reason. Let me erase that from here. Note, see that I depicted the voltmeter like a symbol like that, right? A circle with V total, with V inside the circle and positive and negative terminals. So we're going to need the red cable and the black cable. So it's going to be a total of 2 red cables and 2 black cables for now. So I'm going to put 2 here, 2 red banana cables, 2 black banana cables. Okay, total voltage. Connect the voltmeter in parallel with resistors 1 and 2, right? Resistors 1 and 2. And 2. End of resistor 1, red. End of resistor 1 with red cable. End of resistor 1, red cable. End of resistor 2 with black cable. Okay. Red cable. Positive side of here I'm going to put positive side of the battery. Positive side of the supply, of the power supply. Connect the, let's see here. I'm going to put it like that. Here you go, better. End of resistor 1 is red cable. Positive side of the power supply. End of resistor 2 is black cable. Negative side of the power supply. Negative side of the power supply. Like that. Okay, and that why are we doing that? We want to compare the voltage of the prop that being displayed the power supply with the voltage that being displayed with the multimeter. Okay, and since we're making a measurement at 10 volts, we can go ahead. Here you go, setting at 10 volts, V total. Okay, that's what we are measuring right now. V total should be very close to the V of the power supply. And then we change the voltage to 8 volts, repeat the measurement. Change the voltage of the power supply to 6 volts, 4 volts, 3 volts. All those are measurements. We didn't make those other 3 measurements yet. What you have here are not measurements. Those are results. Okay. Going back. Here you go. Invert the polarity of the power supply. Okay. Let's see. Total voltage. Connect the voltmeter. Okay. Measure the voltage with the voltmeter. Next. Change the voltage in the power supply. I'm going to put PS, okay? PS is for power supply. Power supply. Change the voltage in the PS power supply to 8 volts. Okay? Repeat measurement. to 8, let me put it here, 8, 6, 4, and 2 volts, and repeat measurement for each one with the voltmeter. Okay, here you go. That's that's what I did by exchanging, right, the polarity. And when we do that, let's see, repeat. Let's see. Okay, change polarity of the power supply with the cables, right? The cables. And repeat for 2, 4, 6, 8, and 10 volts. Okay? So that's what we have right in here. Wait a minute, it's not 2, it's 2.7. The power supplies we have there at Lake Harbor doesn't go to 2 volts. The lowest voltage that it provided is 2.7. Okay. And now that, okay, negative, 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 oops, negative, 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 negative. Those are all measurements looking at the screen of the supply, looking at the screen of the voltmeter. That's the difference between this one and this one. Those 2 volts are going to be very close to each other. Okay? V total. So now we are going to, what you're going to do now? We're going to measure the voltage across resistor 1. And let me connect the voltmeter. Let's see, total voltage. Measuring voltages across resistor 1. I call that V1. Measuring total voltage. Measuring total voltage. I'll call that V total. V tot, right? Lowercase, you go. Here you go. Connect voltmeter in parallel with resistor 1 only. Okay? End of resistor 1 with red cable coming. Here you go. Only. Here you go. End of resistor 1 with red cable of the DMM. How am I going to write? Let me see. Let's see. I can write that down in a better way. And connect voltmeter in parallel resistors 1 and 2. Let's see. Red probe. Let's put it this way. Red probe of DMM. Red probe of DMM at the end, at the positive end, at the positive end of resistor 1 is better this way. Okay. And then we can repeat the same here. Black probe of DMM at negative end of resistor 2. Okay. We don't need that anymore. Here you go. That's for the total voltage. And then we can repeat the same that we did here, but just for the multimeter. Red probe DMM at the positive end of resistor 1. Black probe of DMM at negative end of resistor 1. That's because we're measuring the voltage in parallel with resistor 1 only. Okay? Measure let's see, we gotta copy that, right? And paste here. Measure the voltage with the voltmeter. Change the voltage in the power supply to 864 and 2.7. And repeat measurement for each one with the voltmeter. Change polarity of the power supply with the cables and repeat for 2.7, 4, 6, 8, and 10 volts. Okay, that's gonna be V1. And now we have taken care of this column of measurements, V1. And then repeat for what? Repeat for V2, right? That's what we have here for V1. That's how the diagram, right? The schematic, the electrical schematic looks like. I'm showing to you where the positive, right? Side of resistor 1 is located. That's the positive, that's the negative side of the resistor. Resistor 1. Okay. Negative. Now we're going to do, okay, we did total, we did V total, we did V1. Now we are going to do V2. Now we're going to do V2. Spelling out, measuring. All I have to do is to copy and paste this thing for the other one and just make some minor adjustments. Resistor 2, measuring voltage across the resistor 2, V2. Connect the voltmeter in parallel with resistor 2 only. Okay, it's not plural, it's singular. Red probe of DMM at the positive end or resistor 2 between resistors 1 and 2. You can even look here at the drawing. See that? The red cable of the multimeter is between resistor 1 and 2. Okay. Black cable of the multimeter at the negative end of resistor 2. Okay, black probe of the E&M at the negative end of resistor 2. Here you go. Measure the voltage with the voltmeter. Change the voltage in the power supply to 864. And I measure the voltage. Let's put another one here so it's completed. So set power supply to 10 volts, right? If it's not set yet, 10 volts. Let's add this other one in case it's not already set up. All right? Measure the voltage with the voltmeter. Change the voltage in the power supply to 864, 2.7 volts and repeat measurement, right? For each setting, for each of these settings, better. For each of these settings. For each of these settings with the voltmeter. For each of these settings with the voltmeter. Okay. Change polarity of the power supply, right? With the cable and repeat. And then what we get? We get this other column of measurements, V2. Okay. At this point in time, those two are going to be, those two are going to be calculated. And don't forget, this thing is not a measurement. This thing here is a result. And this too is a result as well. This is also a result. So we have one more set of measurements left to do. Measurement of the current. Let's take a look. Okay. So we invert the polarity, right, to take the V2. And look what we did. We measured the total voltage. I'm just repeating this slide, right? We inverted the total voltage. Let's see. Why is the thing here? What's the thing doing here? Okay. V1. Okay, that's V1. That's V2. Okay, negative for V2. Now the next is going to measure the current. We're going to measure the current now. In order to measure the current, we are going to take the circuit apart and put it together. Power supply goes to, notice that I am using a different input here, right? The yellow color instead of the red color. The red is for measurement with voltage. The yellow is for measurement with measurements of current. Okay, so now we are going to start procedure, brand new different procedure. Let's see here, measuring voltage. Measuring current of the circuit, in the circuit. Okay. Take everything apart and start from scratch. 2, connect red cable from the positive, connect red cable on the positive, in the positive terminal of the power supply, in the positive terminal of the power supply. You go. That's what we have right here. I didn't. Let's see here. Let me do it. This one here, right? I'm gonna need this guy here. Okay. And now, see here. I'm gonna get this one. Some slides. Okay. Red cable on positive terminal of power supply. Other end of red cable on the jack of the DMM that measures current. Okay, like that. That's the same as the other one, right? Yeah, let me erase it here. Here you go. Am I recording that? I believe so, right? Yeah. Let's see. Zoom recording. Okay, good. So here you go. And now black cable of multimeter. Black probe of the multimeter. Black probe of DMM on black, in black jack, right? In black jack of DMM. We're not measuring yet, we're just putting the circuit together. Next, other end of black, instead of black probe, let's put black cable into black jack of DMM. Let's put it this way: black cable into black check of DMM. Other end of black cable into positive lead of resistor 1. Resistor 1. Using the alligator clip, right? Alligator clip. You're going to need the alligator clip to do that. Going back, alligator clip goes right in here at this end. Resistor 1, resistor 2 in series, resistor 2 in series with resistor 1 using the prototype board. Using the prototype board. Here you go. Close the circuit. And that's the circuit diagram here. I was supposed to show resistor 1 and 2 here. I didn't do that, but we're supposed, let's see if I have a resistor 1 and 2 here. Yes, I have. Here you go. Let me just copy and paste there. Uh-oh. Here you go. This one goes here. And now we're just going to measure. Note see that the ammeter is in series with the circuit, right? It's not in parallel. If you connect it in parallel, you can blow up the multimeter. You can damage your multimeter. You're not going to damage it because you have actually you have a little fuse there to protect the whole circuit, okay? You're going to burn the fuse, which is far cheaper than the actual multimeter. And now we have current flowing through the circuit. And then what we're going to do, we're going to change it from 10 volts to 2.7 volts, right? Here you go, measuring current in the circuit. Instead of measuring current in the circuit, measuring current, first we set up circuit, right? Here you go. First we set up circuit, measure current, measuring current. And then what we're going to do, we're going to do all those steps here. But instead of measuring voltage, measure the current with the ammeter. Change the voltage in the power supply to 86 PS. PS set at 10 volts. Measure the current with the ammeter. Change the voltage in the PS to 864 and 2.7 volts, and repeat current measurements for each of these settings with the ammeter. Change polarity of the power supply, right? And repeat with the cables, and repeat the current measurement for 2.7, 4, 6, 8, and 10 volts. That would be the negative measurement. And let's go here. No, it's not here. I wanted this one here. And that's the column that we're taking measurements now. So we are done taking measurements. We are done taking measurements. What time is that? 11:50. Let's go a little bit more, right? A little bit more longer. Now we're going to plot some of the graphs here. We're going to plot some of the graphs. What you have to do? Plotting the plot the following graphs. Here you go. V total along the y-axis. Here you go. V total along the y-axis. Okay. I current along the x-axis. Plot the following graphs. The following three graphs, like that. V total versus I, V1 versus I, V2 versus I. Okay? And I'm going to do that. V total, I. Insert. Here you go. That's the current. That's the voltage. And don't forget to get the trend line and display the equation on chart. Okay? I'm getting 3,385.8. And what do? I am going to write down here the slope of this graph. 3,385.8. 3,385.8. And we see the small percentage difference that I get here, right? 0.7% only. Can you do the graph one more time? Sure. Let's do that. I'm going to erase the graph. Highlight V total. Press the Control key. Highlight I column. Okay? Insert, chart, scatter plot. Click one of the data points, right-click one of the data points, add trend line. Display equation chart, display R-square value on chart. Okay? That's spelled out in the syllabus as well. What I did here is, can you do that, Manuel? If your R-square shows equal to 1, just right-click here, like mine, right, showing R-square equal to 1. Just go here, right-click, click that box, right-click it, and format trend line label. Format trend line label, highlight the number instead of general, and increase the number of decimal places until you see a number that's not 1. Okay, so 4, 6. Let's see. Yeah, okay. Let's put 5 decimal places. In my case, it's 5 decimal places. Now I have a number that's not 1. Okay, and let's see here. Plot V total along y-axis, and okay. Get regression equation and R-square value. Square value. Fill R-square on cell, in cell. Fill R-square value in cell. Let's see which cell is this one. Not this one. In cell G28. Okay? In cell G28. Okay? Fill the slope of regression equation in cell let's see, in cell H51. H51. What else? Fill and value in cell. Is that G27? Let's see if it's no, it's not G27, it's G26. Let's see. G26. Yeah, G26. Okay, and fill regression equation in cell G27. In cell G27, fill R square value in cell G28. Fill slope and regression equation. Let's see. No, in cell, okay. Fill slope in cell H51. Okay. And then you repeat for the other ones, right? Here you go. Plot V1 along the y-axis and I current along the x-axis. Along, right? Along the x-axis. Along. See how we're repeating basically what we did before, right? You just hear that's going to be different. Let's see. Get regression equation R square. Let's see which one is going to be, which cell is going to be for V1. Ah, wait a minute. Okay, V total is a different cell. It's G42. Okay, let me fix that. V total is G42, 43, and 44. Right? 28. Here's 28. Yeah, here you go. V1. 26, 77, 28. It's just this. The slope here is going to be, let's see which cell is going to be. This V1 is F51. In cell F51. And then finally we have for V2, plot V2 along the y-axis and I current along the x-axis. Get regression equation R square value, fill and value in cell. Let's see which cell is that gonna be. Cell G34. And the rest is easy, right? Once I have 34 here, all I have to do is 35. Wait a minute, what's going on here? Fill, no. Fill regression equation, okay. Regression equation. Yeah. Fill regression equation. Here too, fill regression equation. Fill regression equation. 34, 35, 36. 36. And then this one should be FGH, right? That should be G here, like that. And okay, so here you go. The other one is V1I, right? And then you gotta do V2I as well. V2I. Insert. Like that. What time is that? 11:57. Okay. Let's do everything here. Add trend line. Display 2960. That's for V1. Let's see for V1. Yeah, that's for V1. 2960. Here you go. 2960. And then we do the same for V2. Trend line 41363. 41363. Did you notice how low, how small the percentage differences are? Those experiments work very well. Those experiments in electricity and magnetism, they work very well, extremely well. And let's not forget, okay, that if you don't have enough decimal places here, you have to change the format of this little square here. Trend line and R square. Any questions? Let's see how you're doing. You have 2 more minutes before you go in our break. Let's see how each one is doing there. Insert. Okay, lab 5, right? Abir, did you manage to download the spreadsheet? Hello, is Abir there? Download L5. Okay, Abir is not answering. Let's see. Nestor, did you manage to download the spreadsheet?
Yeah, I did.
Okay, good. Next, did you plot the graphs?
I did.
Also, all the 3?
Yeah, all 3. That's how
Okay.
far I got.
1, 2, 3 graphs. Okay, that's good. So gotta fill up. Let's see, 1 more minute to go. Did you get the percentage difference?
No, I didn't. I just ended up getting the 3 plots. I just finished the 3rd one.
Okay, so you're working on that, right? That's good.
Yeah.
Okay, so let's take a break now. It's 12 noon, and that's very, extremely detailed here, right? Very detailed here. If you're going to do the actual experiment, all you have to do is to follow those steps here. And break from 12 noon to 12:15 p.m. Okay? And then we pick up where we left. I see you in 15 minutes. Bye-bye. Okay, I'm back here. So let's see how you're all doing, right? So Abir, did you manage to download the report for the spreadsheet for lab 5?
Yes.
Okay, did you plot graphs 1, 2, and 3?
Yeah.
All 3. Okay, you get the percentage difference there at the bottom?
Uh-huh.
Did you get? Okay, well, how much percent did you get?
Oh no, I haven't done the percentage yet.
Okay, so fill that up there, and let's see, next, Monte. Are you there, Monte? Monte, I don't see. Okay, looks like Monte is not here. Isabella? Are you there, Isabella?
Yes.
Okay, you download lab number spreadsheet?
Yes.
Okay, you plot graphs 1, 2, and 3?
I'm still working on 3.
Okay, she's working. Okay, good. Working on 3, right? Working on 3. Okay, good. So let's go. Justus, did you download the spreadsheet? Hello, Justus. Okay, I don't hear from Justus. Let's go to the next one. Alexandra, are you there?
Yes,
Okay, did you download the spreadsheet?
I did, yeah.
Okay, you plot all the three graphs?
I'm working on the second one right now.
Okay, working on the second one. Thank you. So let's go for Benjamin. You finished plotting. Okay. Finished. Okay. What were the percent? Did you get the percentage differences of the three slopes? Not yet. Okay. So let me still working on that, right? Okay. Justus. So did you download your spreadsheet? Yes. Okay. Did you plot all the three graphs? Yes, okay. Did you get the percentage difference of the slope of the three graphs? Still working. Okay, good. So let's go to the Elizabeth Castellano.
I was able to download the spreadsheet and I'm working on the third graph.
On the third graph, okay. Okay, I'll get back to you soon. Let's see here. One. Next. Natalia Córdoba. Hello, Natalia. Okay, it doesn't look like she's in front of her computer. Let's go to the next one. Jacqueline Delgadillo.
Hi.
Okay, did you download your spreadsheet?
Yes.
Okay, did you plot all the three graphs?
I'm working on the third one right now.
The third one, okay. I'll get back to you soon. Jenny Diaz.
I downloaded it, I plotted it, and I know the difference.
Okay, can you tell me what's the percentage difference you're getting?
For the V1, I have 0.6854.
68, okay. 68.
And then for the V2, it's 0.3676.
0.36, okay, 0.37, right? And the other one?
And then the other one is 0.4090.
Okay, 49, right? Like that, or 409?
Yeah, like that.
409, okay, good. So you can see it's very small percentage difference, right?
Yes.
Very small. Okay, so keep on doing the other things, right?
Okay.
And let's see the other one. Valerie.
Hello.
Hello. Did you download your spreadsheet?
Yes.
Okay. Did you plot the three graphs?
Yes.
Okay. Can you tell me what's the percentage difference of each one?
Yeah, I got really large numbers. They're all about 199.
Okay, so there's a problem there, right? Let's see. There's a problem there. Maybe you are mixing up the slope of the graphs. What's the group? What's the spreadsheet of? What's the group number of your spreadsheet there? The last
2.
number in the title of the spreadsheet. What's the last number?
2.
What's that?
2?
Number 2?
Yes.
Okay, so let's see what is the problem. I'm suspecting. Okay, so V total, right? V total and I, you did that, right?
Yes.
Chart, okay, trend line, R square and equation. Okay, the slope is 1661 for V total. Did you get this? Any of those slopes did you get?
I did not.
You didn't? Okay. You're supposed to have three graphs, right? None of
Yeah,
those.
I did. It's just that when I plotted it the way you did, it reversed the X and the Y, so then I had to do it manually.
Okay.
But
Okay, in this case, you don't revert. Okay, in this case, only the previous one you have to invert the axis. In this lab, you don't have to invert. Okay.
okay.
So now you should get the right. Okay, so we found out what the problem was, right? Notice that the I is to the left of the V, right? So in the other graph, in the other lab that we did, the V was to the left of the I. That's why we had to invert that before. But now for this lab, we don't have to do that. Okay? So go ahead and work on that, and we'll get back to you soon. Okay, so we're working on the plot. Juan Escalera. Let's see. Juan doesn't look like he's here. Yeah, it doesn't look like Juan is here. Okay, Escalera. Okay. Take it out. Bianca, are you there? Downloaded graph and work on percentage difference. Okay, good. Thank you. Working on percentage difference. Let's go to the next one. Edwin Gonzalez. Edwin Gonzalez. Doesn't look like Edwin Gonzalez is here. Okay. Eli Gonzalez.
Downloaded the graph, plotted the 3 graphs, and I have the percentages.
Okay, what's that?
0.457 for V1.
Okay.
0.678 for V2. 1.089 for V total.
Okay, good. Okay, so they are very good numbers. Okay, they are less than 5%. It looks like you're in good shape. Keep on doing the rest, right? And let's go to Manuel Pineda. Manuel Hernandez Pineda.
I'm here, Professor. I downloaded the graph and I did all 3 plots, and I'm working on the percentage difference.
Okay, thank you. Let's go for the next one. Samantha, is Samantha there? I don't see Samantha here. Samantha. Next is CJ. Hello, CJ. You download the spreadsheet? Okay. I don't hear from you, CJ. Okay, so let's move to the next one. Amber Lopez, you download the spreadsheet? Downloaded, working on the graphs. Okay. Thank you. Next, Arely Lopez. Are you there? Download the spreadsheet and did graph 1, 2, working on graph 3. That's good. Thank you. Next, Genesis Lopez.
I'm here. I'm still working on the third graph.
Third graph. Okay, working on third graph. That's good. Mary. Working on the graphs. Okay. So, Galia. Are you there, Galia? With a button? I don't see it. Okay, so next is Ramon Olivares. I don't see Ramon either. Ramon, yeah, Ramon is not here. Taylor Fawn.
I downloaded the graphs. I mean, I downloaded the spreadsheet.
Okay, what about the plots?
I plotted all of them.
Okay, do you have the percentage difference?
Yeah.
What's that?
For V1, I got 0.4363.
Okay.
For V2, I got 0.68.
Okay,
and then for V total, I got 1.1.
1 point. Okay, good. They're good numbers. And go ahead, keep on working on the rest. Okay. And what would be the rest, right? So fill the other tables, right? Fill other tables. Let's see. What's important here? Units. Fill up the units, right? And then work on the sig figs. Okay, Jeremy there. I don't see Jeremy here. Next, Stephanie Bramos. Are you there, Stephanie? Okay, good. So let me see. Let's keep up with you here. I have this lab spreadsheet. Download and plot the two graphs. Just need the last one. Okay, good. So yes, and working on graph number 3. Okay. Let's see. Leslie Rios.
Yeah, I downloaded it. I'm just working on the graphs.
Okay, you're working on the graphs. That's good. Jason Straight.
I'm working on the graphs. I think I did something wrong, so I'm trying to figure it out right now. But I downloaded it, yeah. I'm working on it though.
What do you think what do you think you did something wrong?
It's because I plotted the graphs and I have the slopes, but when I put them in, my percentage differences are really high. So I'm trying to figure them out. Because they're like all almost 200% each.
Okay, did you saw what happened to the other student, right? She had inverted the axis. Did you invert the axis as well?
No, I was gonna do that. I was working on that right now.
Yeah, don't invert the axis, okay? Don't invert the axis. Let me see, what's the number there in the title of your spreadsheet? Let's see if we can figure out now what's going on.
Mine is group 10.
10, okay. So let's see here. Okay, V total, let's start with V total, right? Oh, actually, let's start with V1. V1 is easier. Here you go. We're gonna start with V1. You plot V1, right?
Yes.
Okay, so here you go. I'm getting 333.89 for the slope. Is that what you got?
Oh, okay. Never mind. I just realized what my problem was. I was doing the wrong column. I did V soup for some reason. Instead of I. My bad. I'll fix that right now.
Okay, good. Okay, no, that's part of the troubleshooting, right? So yeah, keep that in mind, right? When we do these exercises, it is for you, if you make a mistake, it's for you to recognize what the mistake was. Every time that we go in real life to do a lab, we have to do this type of procedures, right? Sometimes we get something that you're not quite confident that's correct, so you want to troubleshoot. You want to make sure what's happening, right? Why you're getting that result. The result may either be right or may be wrong. Sometimes we get the right result and we think that there is something wrong. It happens too, okay? Sometimes we do get the correct result. Even when you're working in research, even whenever you're doing work that nobody else in the world has done, okay, sometimes you get the correct result, but you don't believe that result. It happened to me when I was doing research at NASA, okay? I got the correct result, and I was not confident about this thing, and it was driving me crazy, okay? And later on, I discovered that everything that I had done at that time was correct, which was just my mindset that was incorrect, okay? Sometimes things like that happen. And then, you can either get the correct result, you can get the wrong result. If you get the wrong result, you have to troubleshoot your spreadsheet, you have to troubleshoot your experiment and see what the problem is, right? So make sure you, use that knowledge, right, for the future. Now let's go for the next student. It's Hema. Hema, are you there?
Yes, I'm finishing up the third graph right now.
The third graph. Okay, good. So third graph is 12:30. We still have 20 minutes to go. Let me give, let's see, let's go back to Abir. Hi, Abir, you plotted out the 3 graphs, right? Last time we talked to you, you plotted out the 3 graphs. Did you get the percentage difference? Hello, Abir. Looks like Abir is away from the computer. Okay, let's go for the next student here. Let's put a star. And
I'm here.
Oh, Abir, okay. Did you get the percentage difference of your slopes?
Oh, no, not yet.
Okay, she worked on that. Okay. Okay, next is Nestor. Let's see. Abir, you have your mic on. Okay, so I turn it off. Are you there, Nestor? Okay, Nestor is not answering. Looks like Nestor left. Nestor Alvarado. Yeah, looks like Nestor left. Okay. Next, Monte, are you there? Monte and Bartian?
I'm here, Professor.
Okay, did you download your spreadsheet?
I've downloaded it and I'm still working on it.
Okay, you didn't plot all the graphs yet, right?
Not yet.
Okay, good. So let's go for Isabella. Isabella, last time you were working on the third graph. Are you there, Isabella? Okay, good. So you got it. You complete all the three plots. You got 0.4, 0.43, and 0.62. Okay. Okay, so those numbers look good. And, you can start work on the units. Next is Justus. Are you there, Justus? Okay, I'm not hearing from Justus. Okay, let's go put a star here under his name. Next is Alexandra.
I'm working on the third graph right now.
The third graph, okay. And let's go for Benjamin. Oops, okay, Justus, so you got it. And let's say Benjamin, right? Benjamin, let me write that down here. So those numbers look good. And then I'll get to okay, Justus, did you get the percentage difference?
No, I'm still working on it right now.
Okay. Okay, but you finished the graphs, right? All the three plots?
Yes.
Okay, good. So
thank you.
Next is Elizabeth Castellano. Elizabeth. Hello, Elizabeth. Okay, good. I was getting the same problem, but it was too big a percentage difference, so I'm redoing it. Okay. You still didn't find out what's the problem. Is that what the problem is, Elizabeth? You still trying to figure out what the problem is? Okay. If you need help, let me know. Let me go for the next one. Natalia Cordoba. Okay, I don't hear from Natalia. Let's put another star here. Jacqueline Delgadillo. Hello, Jacqueline.
Hello?
Yeah. Did you finish the plots? All the plots?
Oh no, I'm working on that, sorry.
Okay. So you should work on the third plot?
Yes.
Okay. So let's see, Jenny. You might be working on the units now, right? Or did you finish the units? Or
Yes, I'm working on my sig figs.
on the six figs. Okay. So work on the six figs. That's good. Okay, good. So let's go for the next one. Valerie.
Hello.
Hello. Did you plot all the three graphs, Valerie?
Yes.
Okay. Do you get the percentage differences?
Yeah.
Okay. What was that?
How many decimal places did you want?
Just two decimal places.
Okay, it's 1.01.
0.1.
0.41.
0.41.
And 1.06.
Okay, good. So very small percentage differences. You're in good shape. What about the units? Did you work on the units already as well?
I have not yet.
Okay, so you're going to start working. Okay, thank you. Juan Escalera, are you there? No, not. Next is Bianca Eloki. Hello, Bianca.
I'm here.
Okay, did you get the percentage differences?
I'm halfway through.
Okay, Okay, so I'll get back to you soon again. Let's see next. Edwin Gonzalez. Is Edwin? No, Edwin's not here either. So let's see. Eli Gonzalez. Last time you gave me the different percentage difference, right? And did you finish?
Yes, units done, sig figs done. I did have a question about confidence level.
Okay, what's that?
So if we're to say the plot points, the number of plot points is our in, looking at the confidence level sheet that we have, my minimum, according to my R squared, is like the very top of the confidence level chart that we have. Like the chart only goes up so far to where my R squared is, and then there's nothing past that. So I was just wondering what to do.
Okay, what's your group number? Tell me what your group number is, please. There in
6.
You said 6?
Correct.
Okay, so let's see. Let's see. I'm gonna plot their graphs. Okay. Oh, here you go. 1, 2, 3. Here you go. I'm gonna let's see if I can plot all 3 at once. It's gonna be a little bit crowded, but at least, right, I get everything in a single. Here you go. Yeah, this one is V total. Here you go. That's at trend line. Here you go. That's V total. And don't forget, you gotta put some decimal places there. Format trend line label. Number. Let's see.
Yeah, I put in 7 just so we're having the same.
Okay. Yeah, you don't need to put 7. 6 is enough. Maybe even 5 is enough. Here you go. That's V total. This one, let's see, is V2. This one is V2. Add trend line, display. Okay. And then this one here, format trend line label, number. Let's put 6, right? Okay, yeah. And V total V2, and the last one is V1. Add trend line. Do the same thing as I did before. Trend line label, number 5. Let's see, 5. Yeah, good. So now I want to know, did you get any of those slopes here? Do you see how the slope that I got? V total V2 is V1, right? For V total is 4,320. Do you get the same slope?
That's V total, but yes.
Okay, good. So let's go V total. You gotta put 4,302, right? Right here in this.
Yeah, I got all of that's got. It's the confidence levels with R squared. That's
oh yeah, that's right. The confidence level. Okay, sorry. Okay, so let's is total of how many points? It's 10 data points, right? 10 data points. Okay, R square for V1. R square for V1 is 0.999559, right? 59. 0.12345. Okay, and now let's take a look at the table. Let's take a look at the table. Okay. Not this one. Confidence level, confidence level. Okay, right from the back, I can see, I don't even need the table for that, okay? I don't even need the table for that. Right from the back, I know that what you're gonna get for the confidence level here is gonna be 1 minus 10 to minus 7. Okay, did you get that?
Exactly. Yeah.
Okay.
That's all we got, though. Yeah. That's where the chart ends.
And then, yeah, and then what do you get? What do you put for max here for the CL max, the upper boundary? Okay, you put number 1. You put number 1 because you know your confidence level is outside that table. It's outside the table on the right side, and you cannot say that 1 minus 10 to minus 8. You cannot say that 1 minus 10 to minus 9. Because you do not have the data to provide this answer. So all you can say is that at the very end of the table, you're going to have a confidence level of 100% or confidence level of 1. And then you put the number 1 right in here. Okay? Makes sense?
Thank you so much. Yes, that makes sense. Thank you.
Okay. So let's go for the next. What time is that? 7 more minutes to go. Okay, so working. Was that Eli, right? I was talking to? No. Yeah, that's working. Good. Manuel Hernandez, are you there?
Yes, I'm here, Professor.
Okay. So did you get the percentage difference?
Yes, I have the percentage difference.
Okay, what's that?
I have 0.40.
Or 0?
0.24.
24.
And 0.74.
Okay, that's good. They are all small values. So did you work on the units as well?
Yes, I'm working on the units.
Okay, working on the unit. Did you finish or are you still working on that?
Oh, I finished them.
Okay, I finished. Any questions about the units?
No, I'm okay.
Okay, good. Sig figs. What about the sig figs?
I'm doing on sig figs right now.
Okay, we're working on the sig figs. Let me see. I have a message from Justice. Let me check this message here. Justice Golden. Units. Percentage difference. Okay, good. Justice, did you finish your units?
Yeah, I just finished right now.
Okay, good. What about the sig figs?
I'm still like working on it, but I'm gonna be finished within before class ends. So.
Okay, good. And
Thank you.
just when it for everybody, right? Not just Justice, everybody. When you go write down the CL, okay. I still see those some problems in there in the CL. Some of you are still, some of you are just playing like that. 1 minus 10 to minus 6, right? And then you highlight here and you put a superscript, okay? Oh man, that's formatting. Let me format this thing here. Font alignment. Let's see. Yeah, they put it in. Okay, let's put. Okay, no format. That's not the one. Should be text. Okay. Oh no, didn't do it. Format. Huh. Okay, I gotta do that again. Let's see. Format. Let's see if you got it. Yeah. 1 minus 10 to minus 6. Gotta do from scratch. Superscript. Okay. I still see answers like that in the CL, okay? And let's say if you have 10 to minus 6 there, the other one is going to be 10 to minus 7, right? I still see answer. You're not supposed to do that, okay? You instead, what we are supposed to do, you have to put an equal sign here, right? You type 1 minus 10, and then you raise to the minus 6. When you do that, okay, when you do that, then don't forget also to reformat back to, not to text. Right now it is formatted in text. You should see here, formatted in text, you gotta put it in number. And now you should get you still didn't get, why is that? Do I have to put a parenthesis here? Let's see if I have to put a parenthesis here. Okay, yeah, now we got it. And here you go, but I put more numbers. Yeah, okay. So that's what you have to do. Don't do something like that. Do not, do not to format it as a text, okay? You gotta format as an actual number. And in order to format as an actual number, what you have to do, you gotta put the equal sign here, and then you also have to raise to the power of whatever you're getting. Okay. And okay, and then it's still not formatted as a number. Let me format back as a number. Now I should get, no, didn't work. Let's see what's going on here. -7, let's see. Yeah, now it worked. Okay, so just as a reminder, and say such. Okay, and what time is that? 12:48. Do you folks have any questions? 2 more minutes to go here. Where I won't be able to go through everybody, but you can finish on your own, right? If you cannot finish on your own, just stay for the office hours. Okay, Houghton. Okay. Okay, here you go. 1. Okay, what are you doing, Houghton? You download the spreadsheet. Behind what? No problem. Okay, did you plot out the 3 graphs, CJ? Did you plot the 3 graphs? 2 and 3. Okay. Okay, so working on the graph. Okay, so let's stop here. 1 minute for 12:50, 12:49, and we can stop right now. And I'll have office hours right now as well. And see you next Monday. Okay. Oh, don't forget, this lab is due next week, right? This lab is due. Lab 5 due 6, 7, May 7, 25. So I see you next Monday. Bye-bye.
Have a good one, Professor.
You too.
Bye, Professor.
Bye-bye. Who's that? Joseph Goldenberg. Hello, Joseph.
Hi, Professor.
You need any help?
I have some questions, but I don't know what you guys were doing before me.
Okay, your voice is coming a little bit distorted. Can you repeat? You have some questions about?
Why does moving current produce heat?
Moving current produce heat. That's because of the resistance. That's because of the resistance, okay? A good model to think about is that if the material has no resistance whatsoever, it's not going to produce any heat, okay? But if there is a resistance in there, it will produce some heat. And there's a very good model that that pictures what happens to the charges inside a wire. Okay, let me see if I can get an illustration here so you can understand. Don't forget that the electric charges, they're the one that produces the current, right? And so those electric charges are moving the wire. The electric charges are moving the wire. So as it
because of voltage.
Huh? Because of what?
Because of voltage, like you're a voltage, you're creating a difference, a potential.
That's right. The voltage is providing some energy to the charges, potential energy to the charges. But the material that the charges are moving, the metal that the charges are moving, there is not a superconductor material. It's a regular conductor. Okay, and because it is a regular conductor, when those charges move, there will be some friction applied to those charges. And the friction applied to those charges is exactly the resistance, the electrical resistance. And this friction, right, that slows down the charge, produces the heat inside the wire. Okay?
So it's friction.
Yeah, it's electrical friction, right? Is the electrical counterpart of the mechanical friction. And that's what resistance is all about. Resistance is just produces friction in the charge. During the motion of the charge. And let me see if I can find a good model. Illustrations. You can see my
So
screen.
theoretically,
Yeah.
okay, and these are considered good inductors, right? But we consider it like copper, something that generates a lot of heat, apparently, is a good inductor. So if I'm able to create a voltage potential that's big enough to outdrive air.
Are you talking about the charges in a metal or the charges in a dielectric? You have to specify what you're talking about, right?
I'm thinking about heat. Like I had this question about heat, about how current. Like I'm learning now about how magnets, how we generate like magnetic fields, right? And we can cause charges on metals to move if we apply certain mechanisms, etc. And I'm seeing how this turns into heat, and that was confusing to me.
Well,
You're saying that.
Go ahead, continue.
So when you move something, when you move like a metal across a magnetic field, then that will induce these charges to move, which because of like these vectors that it always like adds up to.
Okay,
the
so
electrons will generate.
You're not talking about an electric current. You're not talking about an electric current. You're talking about a metal moving in a magnetic field. That's what you're talking about. Is that right?
Yes.
Okay. Okay. And if it produces heat, well, it depends on the situation that you are talking about, right? And let's see here.
Because I understand mathematically all those things until we get to the current to the heat, right? Like that's like it all mathematically makes sense, right? If you move something across with a certain force and you move like you can calculate using like the formulas that we have to get to the Biosavart, and we can use that to calculate how much. But once you get to current, how do you get like it's all like that's where before I start seeing it, like friction, and friction causes heat. Thank you for that. It makes a little bit more sense, but it's a lot.
Okay, I'm still trying to understand your question, right? So let's see. Initially, I thought that you were asking for a current, right, in a wire.
Yes, current. Why does it generate heat? And
that's produce heat, right? That's produce heat. Yeah, that you understand, right? And it produce heat because of the wire resistance, right? That you understand, right?
Even if it's alternating current.
Oh yeah, even if it's alternating,
like
even if it's not alternating current. Just think about the not the LED lamps that we have nowadays, but the older lamps. How do you call that? I always forget the name of the lamp. The regular lamp that has a filament. How do you call it?
A light bulb.
But the light bulb. There's another name for that. Let me see here. Regular light bulbs. How do you call them?
And also, like, why only so it only generates heat over there? Why doesn't it generate heat throughout the whole wire, right? Like, because the whole wire is a better conductor.
Well, here you go. We call it incandescent light bulb. Okay. We call it incandescent light bulb. Okay. It all depends on the resistance. Okay. It all depends on the resistance. If you have a circuit in which part of the circuit has a very low resistance and another part of the circuit has a high resistance, then the heat is going to be concentrated on that element that has a high resistance. Okay. In the case of incandescent light bulbs, for instance, here you go. We have here incandescent light bulbs, right? Do you see those two wires here? This wire here and this wire right here? That's all part of the circuit. But in between those two wires, you have another wire made of a different material that has a different resistance. Okay.
So
And
why doesn't it go through the air? Because the air is too high of a resistance?
What do you mean that it goes through the air? The heat doesn't go through the air? That's what you're asking?
Why does it? You're saying that. So it's a higher resistance than that, but yet a lower resistance than the vacuum around that filament.
No. Wait a minute. We're talking about, here you go. Let me do another drawing here. Let's see here. Oh, here you go. I'm gonna get this circuit here, right? And consider insert.
Like the second you get the heat, that's where like
Here I'm
that's
gonna
where like theoretically you throw me off like the
so here you go. A light bulb is something like the following. Here you go. Is a source, right? A power source, that is the voltage, and the light bulb is just like a resistor.
yeah.
Okay. It's just like a resistor. That's what the light bulb is. And so let's say this guy here is a light bulb. Okay, in order to represent a light bulb, we represent the light bulb by a circle. Anything that has a source, is represented in this way. No fill. Okay, make sense? Okay, right
Yes.
here is that how current passes through this device. You have a current because those wires have very low resistance. Okay, this wire here have very, very low resistance. They are not going to heat up. They're not going to warm up. However, because this region here of the circuit has a high resistance, then this one is going to warm up. And sometimes it's going to get so hot, so warm, that it's going to start to glow. Okay? That's what the incandescent light bulb do. That's how an incandescent light bulb works. It produces
Just because it gets
much
just
heat.
because resistance. So if there's so much resistance, why does it still go through? Like if there's as much resistance as you're claiming, right? Like why does it still go through yet? Why doesn't the resistance just stop it? Like,
oh, you mean the current?
Yeah.
Yeah. It
because
doesn't stop.
I know the mathematical.
Yeah, it doesn't stop because you still have a voltage here, a voltage source that's producing some that's giving some energy to the lamp. Okay, that's why. Let me see here what's going on here. I cannot invert.
So what's that number theoretically? There should be like a number.
A number
I get like Ohm's law, like and how you get like like V equals IR, and you can calculate like the.
Yeah, so there is Ohm's law, right? V equals
But at what point does it break down? At what point does it stop working? At what point is the resistor zero? Like at what point does it become nothing?
Okay, well, at what point the resistor breaks? That's what you're asking, right? At what point does the resistor break? Something like that, right? Is that what you're asking? Okay. Well, it all depends on the material. Okay, sometimes the material start to oxidize. It's and then that's why they put the light bulb inside an enclosure that has no air there inside. Okay, that glass.
Because if there would be air.
The glass enclosure of the incandescent light bulb. Why does the glass enclosure?
It's under no pressure. Like I know
That's
that.
right.
Like I've heard about that. That it's under it's a vacuum, and like they try to because pressure.
That's right.
In the atmosphere, like you don't have any like nitrogen or oxygen to rip off electrons to create that.
That's
but what
right.
would that? Is that represented in V equals IR? Like in Ohm's law, can we see that? Like, is that? What can I mathematically tell you like when it's gonna get there? Like when is it gonna break? Because according to the law, you should be able to infinite, right? Like
yeah, it's a more difficult problem to treat because it depends on other things. Okay, so if somehow that vacuum inside the lamp, is not as perfect, then air is gonna seep into the bulb, right? And the oxygen is going to start oxidizing oxidizing the resistor. And when you start oxidizing the resistor, the resistor is going to become very brittle and it's going to break because of the oxidation, okay? That's why they have to keep that resistance there in almost vacuum, okay? That's for, that's for incandescent light bulbs, right? For the other types of light bulbs is different.
It's just a resistor that.
Okay. Okay, so here you go. The wire resistance. Just think about an incandescent, there you go, incandescent light bulb. Okay, think about incandescent light bulb. Okay, here you go. The incandescent light bulb gets very hot when we pass a current through it, okay? Gets very hot, okay? If the filament, right? If the filament of the bulb were to be exposed to air, the filament would oxidize more readily because of the temperature of the filament. Okay, once oxidized, right? Oxidized, it will break down more easily. Okay. This part of oxidation we cannot predict by theory. Okay, we do not cover something like that in a course of physics. Then it becomes more like a course on materials, properties of materials. Oxidized. Does it help?
I'm at the point now where I'm like learning about. So it's weird to me that I can answer something mathematically, but I can't answer something in common sense.
Try to put in writing exactly what you want to ask. Maybe that's the problem. Try to so to organize your thoughts more clearly, because so I can understand what so I can help you better, right?
Oh, Professor, I had a quick question about the lab today.
Yeah, what's that?
For the should we add axis titles?
Yes, yeah,
and
that's
then
what
it would
title,
be
the
volts
title in the
for
unit.
Y. Yeah, okay. It would be a volts for Y, and then what would it be for X?
Oh, X. What do you put in along the x-axis? What do you put along the x-axis? Think about that, right? You are plotting. Here go volts along the y-axis, and what are you plotting along the x-axis?
Oh, okay. Yeah, I got it. Okay.
All right. So.
And then for the units on that graph right there, on that chart, on the very last one to the right.
Very last one, right here. What about it?
Oh no. The units at the very top with the numbers.
Very top. Okay, yeah. Here you go. The unit of resistance, right?
That one's gonna be omega, right? For the
Omega.
unit.
And what about this one? Which unit is going to be for this one?
Omega 2? I don't remember.
Yeah, they are both resistor.
Right?
Resistor 1, resistor 2, right? So it must
Yeah.
have the same unit. It's just
What about the one right there? The unit right there on under quantities? Yeah, that
here?
Yeah, on the very right. Yeah, that last one. Is it going to be V over A?
Yeah, and V over A is what? What's the unit of V over A? You can do dimensional analysis using Ohm's law. If you do dimensional analysis using Ohm's law, you find out what's going to be this unit. Okay.
Got it. Yeah.
Okay. Here you go. Let me help you further. Let's see. Here you go. Ohm's law, right? Ohm's law is V equal to Ri, right?
Okay.
Right. Here you go. Unit. Then you use dimensional analysis. Here you go. Unit of V is equal to unit of R times unit of I, right? Here you go. Right? What's the unit what's the unit of V?
Joules per coulomb.
Yeah, joules per coulomb, but joules per coulomb has also another name, right? What's the other name? It also has another name. Volts. Yeah, here you go. Volts. What's the unit of I?
Current is amps.
Amps.
And that's joules per second. No, coulombs per second.
Yeah, that's right. Which is coulomb per second. But let's leave this way, right? Let's leave this way. You don't have to.
This connects directly to my question. Like this is like, right? Because I'm thinking about joules per coulomb are moving, right? Like it makes sense to me. So far, the story makes sense, right? So when we get to that,
yeah, joules per coulomb is voltage, right? And when you divide by A, right, amps, you get the unit of resistance. Okay, Manuel?
Okay,
Manuel,
got it.
Yeah. And the unit of resistance is what? Is the omega, right? There's a relationship between the units.
Okay, thank you.
But you know, you can go even further than that, just like Joseph said, right? You can put
what is omega? Like, how would you describe omega in
omega
English?
Is the unit of a resistance. Is the unit of resistance.
So is that like the negative of joules per second, like or like joules inhibited per second?
Oh, it's
right,
volts. It's volts per amps, right? So here you go. Volts is joules per coulomb. Amps is going to be coulomb.
Joules per second.
No.
Coulombs per second. Yes.
Coulombs per second.
Coulombs per second. Yeah.
Okay, and then when you solve that, what do you get? You get joules second, joules seconds, right? Second upstairs, right?
Yeah.
Then becomes coulomb square downstairs. Becomes coulomb square down. Okay, so that would be another way of writing down.
Joules seconds.
Yeah, joules seconds over coulomb square, and then you can go further than that. You can here you go. Joules is what?
Joules in Newton meter.
Newton meter. Newton is what? Kilogram meter per second square, right? You can cancel out the seconds with seconds. Let's see. You don't get any simpler than, okay, yeah. See, you can cancel this second with this seconds here.
No, because Professor, I'm thinking about how this ties into resistance, how this ties into me seeing a light bulb, right? How this ties into the current moving right now, magnetics, how I'm doing that to do that. It's just, I'm trying to make physical sense of it also, not just,
Okay. Okay, but yeah, that's just the easiest way would be volts per amp. You know. Now the question of the heat, right, that you're mentioning, you know, just think in terms of electrical friction. That's what resistance is all about. Is electrical friction. The charges, when they are moving through the metal, they keep on colliding with some dirt there inside, keep on colliding with some other atoms. They are slowed down by the electric field, you know, and that produces heat. That's the best way of seeing it at a microscopic level. Let me see if I have, I used to have a drawing of that. No, it's not here. It might be here. Electric circuits. Here you go. Maybe it's here. Let's see if it's here.
Because also resistance opens itself up. Resistance is like 1/ρ, right? The length, the 1/the length, and like the resistivity constant, right? So there's also.
Go ahead, finish. Okay, here you go.
Sorry.
Here's an illustration of the motion of the electrons inside a wire. Okay, it's just like a pinball, a ball in a pinball machine, bouncing back and forth, back everywhere, you know. And as it moves along this this wire, it loses some energy. When it loses some energy, the energy that it's losing, like the kinetic energy it loses, it's transformed into heat. It's just conversion of one type of energy to another one.
Say that again. Like it goes from what to heat? From
you know, here's a model of the motion of an electron inside a wire.
Yeah.
Okay, it's this electron that's producing a current. It's the electron that's producing a current. Okay, the electron, the charged particle, they don't move nicely in a straight line here in the wire. No, it's not how they move it. The way they move is just like in this random fashion. Okay, it's like a zigzag format. You know, it goes this way, get bounced up, and then move backwards a little bit, moves forward. You know, and just keep on moving this zigzag fashion. Along this route, the electron, they lose energy, they lose kinetic energy. Okay? And this kinetic energy is transformed into heat. That's the best model that you're going to get of this type of motion.
When I move a piece like from here to here, in my mind, that's a lot more okay, but it's not at a higher velocity specifically because they're moving in these little things at much greater a velocity than we're seeing. Then I can move from here to here essentially.
Mm-hmm. Okay, and let's see. Are you talking about a macroscopic object or a microscopic object?
Yeah, right. Like why don't I see like why doesn't a metal get super hot if I move it from here to here physically in the macro, right? Like I'm also moving these electrons that are in there theoretically.
I know,
it's
but
a displacement. It's not a velocity.
Are you talking about a metal moving in a surface? Is that what you're talking about? Like a metal moving like that? Is that what you're talking
about? No, not across a magnetic field. Just
across
moving. Just.
Uh-huh.
No,
okay.
Staying out of magnetic field for now.
Okay, across the magnetic field. I see. Okay, yeah, if you move a metal across a magnetic field, the magnetic force is going to separate the electrons inside the metal, okay? And you're going to generate you're going to generate a current. Whenever you have the charges moving inside the metal, you're going to generate a current. And once you generate a current, yeah, you're going to have a heat. You're going to have the heat due to the current that the magnetic field is producing in the wire, in the metal. Okay, that's what happens. think a little bit. Let me help Benjamin. Benjamin, do you have a question?
Yeah, right.
Think a little bit. Let me help these other students here quickly. Benjamin, do you have a question? Okay, yeah, it looks like a. Oh yes, what's that? Lab 2. Do we have to fill up units on the last table? Yes, that's right. Here you go. Let me share the screen here with you. Last table. Okay, here you go. You have to put the units here and you have to put the units here. Cell I51 and cell I52, okay? The unit of the slope and the unit of the delta. Okay? Here's the unit of the slope and here's the unit of the delta. Okay, and here's the numeric value. Here's the numeric value of the slope, numeric value of the slope, numeric value of the slope. Okay? Okay, good. Okay, so and let's see. Let me see if I can. You're talking about a metal moving in a magnetic field, right, Joseph? That's what you're talking about.
Yeah, that's where I was having trouble to connect all the pieces.
Okay,
Yeah,
so,
that's where.
okay, so let me do a. This is not difficult to explain. Let me see if I can have a drawing here. This is not difficult to explain. Okay, not this one. I need another one. Illustrations, electric field, magnetic field. Okay, let's see if this one has an illustration here. I can show you. Okay, this part here you understand, right? This part here you understand. Here you go. Electric charge in a magnetic field, right?
Yes, an electric charge in a magnetic field.
Yeah.
Experiences a force from the force, whatever, like the shadow.
That's right. Experience
and that's
a magnetic force.
Yeah, this yes.
Okay.
Theoretically, this makes sense. Like,
okay. Now you have to know that to understand this other level here that we're discussing. Okay.
The right-hand rule and how the direction of where it causes the magnetic field, like line that it's going to look at from that specific. I mean, it doesn't make sense to me also, like how it becomes a circle.
Okay.
You know what I mean? Like how.
Why does it become a circle? It becomes a circle because the force is perpendicular to the velocity. Okay, that's why it's perpendicular to the velocity. So,
but also perpendicular to the magnetic field.
The force is also perpendicular to the magnetic field, and the force is
which is why we're taking.
Yeah, and the force is constant because the magnetic field is uniform. Okay.
Yeah.
It's constant because the magnetic field is uniform. So here you go. That's the velocity. That's the force vector. The force vector is like that. Okay. That's the force vector here in this specific case. When you have a force perpendicular to the velocity vector, the particle is going to describe a circular motion. Okay? This force here acts. Once you have a force perpendicular to a velocity vector, the particle is going to change direction of motion. Okay? And by changing direction of motion, I mean it's going to describe a circle, a circular trajectory. Okay? That's why it's a circle. That's why it moves in a circle. Because of the angle of the velocity vector and the force acting on the particle.
Can we describe that in the big world? Like if I move like a ball from here to here and it experiences a force.
Well,
why does it go on a circle?
Well, think about that. Is that true? Think about that. If the force were like that, what's going to happen to the velocity of the particle?
It's going to go to the left.
I know, but what's going to happen to the velocity? It's going to increase. It's going to decrease. It's going to remain the same.
It's going to increase.
It's going to increase. Okay, good. Okay, now What about here? Can the speed, can the velocity vector increase in magnitude here?
No, but why did so?
No, it's not going to increase because the force is perpendicular, right? The speed does not increase, but something else must give. Something else must give because we have a force here along this direction. What's going to give? Is the direction of the force of the velocity that's going to give. Okay? This force is going little by little produces a velocity along this perpendicular direction. Okay? It's going to start at t equal to 0. The velocity along this line here is going to be 0, right? A little bit later on, it's going to be something else. A little bit later on, it's going to be a little bit more, okay? So this force is producing a vector component, a velocity vector component perpendicular to this other one here, this other velocity vector. And the result is circular motion, ends up being a circular motion because it's a constant force.
So it's experiencing two forces, one coming from, in simpler terms, like one coming from, like one heading straight into
It's not two forces, it's two velocity vectors, okay? This velocity vector
two velocity vector.
Yeah, this velocity vector was already here. This force is going to produce another velocity vector component. Okay, this force here is just like your regular physics 37 physics 37, right? So here you go. Let me do. Oh, like that.
Velocity vector.
Here you go. Here's your mass, right? Your particle. And now it's initially at rest, right? Suppose it's initially at rest. And then I decide to apply a force to this particle. The force, right? And this force is initially initially at rest, velocity is equal to 0, right? And this one here is going to be a force different of 0. Force greater than 0, right? Initially, this object is going to be here, right? A little bit later, you know, this force is going to move this object to the right, right? And the velocity is no longer going to be 0. The velocity now is going to be v1. V1.
Plus, yeah.
Okay, subscript v1. A little bit later on, here you go. The same force still keep on acting. Okay, the particle is going to move further to the right. It's going to produce a velocity v2, right?
Okay.
And so on, right? Here you go. And then we can even play the movie. Here you go. Here, 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 right?
Yeah.
Okay. And then what's going to be the next movie? The next movie is going to be like that. The next, you know, here you go. Okay, 0, v1, v2, and that should be v3. Okay, that you understand, right? No secret here, right? Right?
Force is going to create a velocity.
Okay. Now we are going
to. If the force is constant?
Huh?
Are they both changing? Is velocity changing and force is changing?
No, the force is constant.
Force constant.
The force is constant.
Okay.
Because the force is constant, the velocity must change. Okay? Because the force is constant, the velocity must change. Okay. Okay, here you go. Force constant.
Yeah.
Okay? Now we are going to do something different. That applies to that electric charge that you mentioned. Okay. Okay, so here you go. 1, 2, 3, 4, right? Okay, now we're going to do something different. I'm going to copy all those 4 slides and place here. Okay? Not only are we going to have a constant force, but we are also going to have an initial velocity in this other direction. okay, in a initial velocity in this direction. Okay, and that's not gonna be, there's gonna be different of 0. Here you go. Okay, and this velocity here is constant, no friction whatsoever. Okay, so what you're going to have, you're going to have a combination of two motions. You're going to have a combination of this type of motion here along.
But then the velocity is no longer in that way.
Oh, wait a minute.
You changed the definition of it, no? Like.
Oh, wait a minute. Let's go slowly here. Here you go. Let's see. You know what? We should do in the following way. We're going to take out the force now. Let's take out the force. Okay? Let's say the particle is just moving with constant velocity in this direction. Okay?
Okay.
Let me see if I got it the right. If I got it in the right. Yeah, I got it in the right there. Okay, good. Okay, no force whatsoever. So initial is going to be here, right? A little bit late. It's going to be.
It's going to go down, whatever. Like.
It's going to go down.
Okay.
Okay, a little bit late. Okay, a little bit late. Okay, now let's see. Let's play the movie. 1, 1, 1, 1. Right? Here you go.
Okay.
That's okay. And let's play the other movie here. Here you go. Because you have a force, right? The velocity is changing, and the displacements they will be increasing, right? The displacement will be increased because it's being accelerated. Gosh.
The vector of it that goes that way.
Okay.
So when we have both of them interact.
So here you go. 1, 1, 1, 1, 1, right? Do you agree with that? Just a force.
Yeah. Okay.
Okay. Here you go.
So when you add them up.
When you add this type of motion with this other type of motion, you're going to have a
circle, like
a different,
not circle, like a hemi.
Yeah, a different path. Okay, you're going to have a different path. Okay, so it's gonna be what? Let's see if I can do that.
You're gonna have like how we described like centripetal.
Yeah, we're gonna get there. Hang in there. We're gonna get there. Here is just one. Now we have to combine those two type of motion. Okay, we have to combine those two type of motion. One is constant force along the x direction. The other is zero force along the y direction. Okay, yeah. So here you go. Next one. This one should be combined, and this one too. I need to combine that as well. Here you go. Okay, right in here. And then let's see, 1, 2, 1, 2. This one. I'll copy this one. And I paste right in here. See that? Here's the motion along the x-axis. Here's the motion along the y-axis. Okay? The force is still constant to the right. The force
then it should just be a 45 degree down, whatever.
Okay, the force is still constant to the right. So keep on, let's keep on going. Here you go. This other one here. Okay, here you go. 1, 2, 3, right? And the other one, let's see. 1, 2, 3. Here you go.
But this is also, and what about the z in this case?
The what?
We're not even concerning ourselves about the depth of it yet. We're only talking about like the. In 3D, if these forces
No.
continue,
We are doing two-dimensional motion. We are doing two-dimensional motion. We're not doing three-dimensional motion, okay? We're not doing three-dimensional motion. Okay, so here you go. This time with a force constant, the resulting motion is going to be, here you go. It's going to be the following. You can
if they're both equivalent, they're going to be like a straight, like a 1 degree, like what, 1.
Okay, here you go. Right here.
Rise over 1 are going to be 1/1. If it's
the other one. It's like a two-dimensional motion, okay? Here you go. Like that. Okay. I even going to go. Now I'm going to remove the unnecessary points. I will remove this one. I will remove this one. I will remove this one, and I will remove this one. See that the pass of this guy is kind of a curved pass. Okay. We can go for the next one too. The next next screenshot. 1, 2, 3. Right. The fourth. That would be the fourth one. The fourth one is here. No, that's not the fourth one. That's the third one. Okay, that should be the fourth one. Yeah, that should be the fourth one. Okay, you can do that with PowerPoint.
Okay, so how do we get from this to a circle to the right-hand rule?
Oh, okay. Wait a minute. When I get there, is this force changing direction? Yes or no? Is this force changing? Huh? Is this force here?
No, we're saying that it's constant, right? We're saying no. If it's constant.
No, it's the velocity that's changing. The force is not changing, right? The force is not changing. It's the velocity that's changing, right? So how do we get to the motion in the? Let me put that here. Here you go.
Isn't velocity changing the acceleration? Like
what?
Isn't velocity changing acceleration?
Yeah, it's accelerated, right? Here you go. Okay, because the force is constant to the right, you get this type of pattern, this type of pass. Okay?
Over time.
Over time. Now, what happens if the force is not constant? What happens if the force keep on changing direction as the particle is moving? Okay? Every time, every time that charge moves, the force is going to change direction, right? Let's see if I can get the. That's why it leads to a circular motion. It leads to circular motion because the magnitude of force is constant. But on the top of that, the direction of the force is changing as well. Okay, let's see here. Okay, right in here. Oh, yeah, here you go. Right in here. Look what happens. The particle is going to move to the left in the horizontal direction, but it's also going to move upwards in the vertical direction. Right? Once the particle moves upwards in vertical direction, what's going to happen to the force? The force is going to change direction as well. And the force will always be perpendicular to the velocity vector. Because it is V cross B. Because it's V cross B. Okay? The force will always be perpendicular to the velocity vector. And it ends up being circular motion. Why it ends up being circular motion? Because the magnitude of the force is constant and the direction of the force is perpendicular to the velocity vector. That's why it ends up being circular motion. Okay? So I'm going to write that down here for you. Here you go. A particle. Here you go. A particle with a velocity vector perpendicular to a uniform magnetic field, right? A charged particle will experiment a magnetic force that is simultaneously perpendicular to the velocity vector, to the velocity and magnetic field vectors, right? That you understand, right? It comes from the law. Here you go.
Yeah.
It comes from the law that you saw. Here you go. F
Because QVB,
yeah,
QV cross V.
that's right. Q D cross B. Like that. The force is perpendicular to the velocity vector and to the magnetic field. Okay? So, but this force is also changing, is giving a perpendicular, a component of displacement along the force as well. Because this force will always be perpendicular to the velocity vector, the only type of motion that you're going to find is going to be a uniform circular motion. Okay? So here you go. Let me write that down here. A charging particle velocity. Okay, here you go. Because the force is perpendicular to the velocity vector, comma, the speed of the particle will be constant. Right? Do you understand that? Because the force is perpendicular to the velocity vector.
Is there an experiment where I can see this?
Oh, yes. Let's see here. Yeah, we do have. Let's see. You're taking the experiment with Crawford, right? You're taking the lab with Crawford?
Yeah.
Yeah? Yeah, we
Yes,
have equipment that shows that. Yeah, we do have equipment there in the college that shows that. You can look into the internet, in the YouTube. Maybe you'll be able to find it. YouTube. Okay, so here you go.
Like proving that it. Because I can repeat to you the right-hand rule, but I can't. But I don't understand. And especially in 3D, when you're talking about like what the world is, and over time, also the second you start taking that into account, like
But well, this wait a minute. This motion here is not 3D motion. This motion here is 2D motion. Okay.
Yes.
It's 2D motion. Okay. So you don't have to worry about 3D motion, but it ends up being a circular motion because the force will always be perpendicular to the velocity vector. Okay. For two reasons, not just because here you go. Because the force is perpendicular, the speed of the particle will be constant. Okay. Because of the magnetic force law, comma, the force will always be perpendicular to the velocity
and the magnetic field.
Okay, here you go. That should go right here. Okay, because, and then I'm going to put it always. Because the force is perpendicular to the velocity, the speed of the particle will be constant. Okay, the speed. Don't forget the speed. Okay.
Because what? Why will the speed be constant? Because the force is perpendicular.
Because the force is perpendicular to the velocity vector. Because the force is perpendicular because of this equation right in here. Okay. Because the force is that thing about the force doesn't do any work on the particle. It does not do any work on the particle because the force is perpendicular to the velocity vector. Okay, that's why.
Why?
Oh, because of this one, all because of that. This thing is a law. Okay, there's no why for that. This is a law. People discovered that the universe works like this way. Okay, there is no, there is no. It's just the way it is. Okay, it's just like a law of physics. there's no Y for F equal to MA. Okay?
No, can we measure this? Can we measure this? Is it like what an experiment can I do to verify?
Oh yeah, people did this experiment over and over again. That's why we study it. That's why this type of relation has been verified over and over again. Yes, and there is some demonstrations. Let's see here. Magnetic force. Magnetic force. You can go to YouTube in an electric moving electric charge. Okay, now moving electric charge. Here you go. Magnetic. Let's see if they have experiment here.
Any recommendation?
Oh, they have some nice. Here you go.
I recently had a lot of fun making simulations for how the electric field responds to a moving charge. It was all for a longer video on YouTube that covers
this one. Let me see. This one.
Here, I just thought I'd share with you some of the pretty.
Yeah, you don't want to watch this one. This one is too complicated. Maybe this one here. Let's see. Okay, here you go. Magnetic fields, velocity vector. Okay, here you go. B cross B. B cross B. Forces upwards. Okay, see that? Yeah, I like this one. B cross B. B cross B, the force is going to be along the z-axis. And this force will always be perpendicular to the velocity vector. That's why the particle undergoes uniform circular motion. And so there is one more, right? Because it is always perpendicular to the velocity vector, the speed of the is always perpendicular to the velocity vector. The speed of the particle will always be constant. Always be constant. And what else? Because the magnetic field, here you go, let me stop the thing. Okay, because the B field is uniform, the force will, the magnitude of the force, the magnitude of the force will always be constant, the magnitude, okay, but not the direction. Okay, we're running out of time here. Okay, that's what you have to to consider. Okay, that's why because of those three reasons, that's why you end up having uniform circular motion. Okay. Constant speed, constant force, not constant force, constant magnitude of the force.
Is there any equivalent to this in the bigger in another context?
Right. Let me finish here the idea. Perpendicular to the velocity vector. Okay. What you're asking?
Like I want to see this in the actual, not just the.
Yeah. Like I said, there are some videos here in YouTube that you can look at. I didn't find that yet, but there is. Let's see. This is just a simulation. It's not an actual experiment. But we do have maybe this one here. Let's see if this one here.
Welcome to the demo prep room. We're sitting here in the dark because we're going to show you the particle beam doesn't need to go in a circle, put it into uniform magnetic. So this is an evacuated glass.
I can watch them. I'll watch them on my own time. Like, what is it, physics? What is that, professor?
Easy to throw electrons off of them.
Let me look up that.
Okay, I'm gonna give you the link for that one.
Please.
Yeah, this one should be a good one. But then another one is this one. There's a bunch, okay? Magnetic force is a moving electric charge, See that? Here you go. Here's the beam of electron.
You're seeing the beam because it's exciting a little bit of gas.
Let's see. Let me send it.
The gas. So it's there because the beam is shooting through the gas. So we're seeing the electric beam. Now we know that if we bring a magnet nearby, it'll deflect the beam. So here's my north-south bar magnet.
There you go. That's the link.
One pole pushes it up.
Thank you.
Down.
Okay. Okay, do you see that?
Thank you. Yes.
But there's more.
Thank
That's
you.
one of them. Okay. So take a look at that. What we're here to do. And I gotta go now. And
No, thank you. Thank you, Professor.
welcome. Okay.
Have a good
Bye-bye.
day. It's nice to see you. Thank you.
Welcome. Man, this.